Hey, welcome back to Fat Mama Physics. This is the third video on impulse in which we will go over more examples, but before we do that, we should answer the question that we had at the very beginning of this series, and that is the parkour roll. So here I have the shot that the video I showed you at the very beginning, where I have this guy jumping off from a very tall building, and going into this parkour roll without sustaining any injuries. Of course, don't do that at home. And the question was, how was he able to not hurt himself? And we also talked about things such as car safety, such as seatbelts, airbags, crumple zones. If you're not sure what a crumple zone is, I have a few pictures here that I can show you. So take a look at this car over here where I did a Google search. Notice the front of the car has been pushed and compressed all the way back without the rest of this car structure sustaining any sort of impact or any sort of damage, especially this passenger seat over here. And here I just got a video just to quickly demonstrate what that means.
The beginning of the crash, what we get is the barrier loading the front bumper, and a lot of those forces are then transferred directly to the front longitudinal structure inside that surround the engine compartment, and then we start pushing in directly into the wheel and the steering components, which then push directly into some of the occupant compartment areas.
Okay, and here is that video. So why do we have those? And how does all of that help reduce the injuries on the passenger during a car crash? And to do that, to answer all of these questions, we're going to help us visualize this using a force time graph. This force time graph is on the egg throw, and so maybe some of you have done this experiment or have designed a structure to help to wrap around the egg or whatever it is, that when you drop the egg from a tall building or a high place, it's not going to break once it hits the ground. This is very similar, but here we have an egg that is being thrown against a wall versus the egg thrown against the bed sheet. So either a wall here or a bed sheet. Okay, so here I have two graphs, and this is a force time graph. I have force on the y-axis and time on the x-axis. Before we talk more about this graph, let's just get something straight here. If I have an egg going towards the wall, let's say I'm throwing at some speed u. So when this egg approaches the wall or the bed sheet, whatever it does in the process, this egg's going to go splat on the wall, reaching a final velocity of 0. And same thing when it hits the bed sheet. It's going to go into the bed sheet. Bed sheet might kind of recoil a bit, but at the very end, the egg still comes to rest with a final velocity of 0. Now, if we have the same initial velocity and the same final velocity, same egg, which we have a change in, and times the change in our velocity there, our change in momentum is going to be the same for either of these cases. When we have the same momentum, we also have the same impulse. We also know that impulse is also equal to the force acting on an object times the time that it was applied. So that's force times time. Now, what dimension on what property on a force time graph is force times the time? If you're thinking about area, which is right there, yes, the area is the impulse. So the area underneath this force time graph, this gray shaded area here, is the change of momentum of my egg. And notice the area underneath both of these graphs is relatively the same if you count all the squares. So then we know that the same egg undergoes the same change of momentum, same impulse. What's the difference? The key thing that you see in these two graphs, and you probably observed already, is the fact that if an egg is thrown against the wall, it sustains a very high amount of force, but over a short amount of time. Versus if it was thrown at a bed sheet, that impulse is spread over a longer period of time, so the the bed sheet doesn't need to exert as much force on the egg. So we have a small force exerted over a longer period of time. And of course, you have a big number times a small number in both cases, FTs. And so when you multiply both, you multiply them to get your impulse, you get the same value for either case. So then we can see that by using a bed sheet, it helps spread out that impulse over a longer time. It helps distribute that force. It helps distribute that impulse. So over a longer period of time, you don't need as much force to stop the egg. And that's the same concept here when we are talking about a car crash with seatbelts or without seatbelts, as well as the crumple zone and the airbags and whatnot. So here we have a passenger A here, and this is also a force time graph. Passenger A kind of sustains a large amount of force in a short amount of time without seatbelts on. And then here we have a passenger B who is wearing their seatbelts. Here we have a smaller amount of force, but that force applied over a longer period of time. If we also take a look at the parkour roll, notice that if I'm just going to quickly play this here. So take a look at how much that force was allowed, his momentum was allowed to dissipate over a longer stretch of time, as opposed to him just dropping on the floor and just hitting himself and not going into that roll at all. So that is the idea behind this impulse. You can either go big and go home, or you can take a small amount over a longer stretch of period of time. But no matter the case, you get the same amount of impulse, okay? Now, let's apply what we just learned to a question here. And again, I'm going to do question 5. You're going to do question 6. Question 5 is a passenger without seatbelts. So here I've simplified our graph above into a rectangular shape, so it's easier for us to calculate. So it's just a model. It's probably not very accurate. So the graph below shows the impulse experienced by a passenger without seatbelts. Calculate the impulse felt by the passenger. And we just learned above that the impulse on a forced time graph is the area underneath this graph. So between this graph line and the x-axis right there. So the area here of a regular rectangle is your length times your width, in which I'm going to use a length here as 80. Oh, but wait. It's not just 80 newtons. It's 80 kilonewtons. Don't forget to read your axes properly. Whenever you see the word kilo, that just means 1,000. So I'm going to add 3 zeros here. And that's going to be multiplied by the width here in case it's the time. So the difference here between 0.1 and 0.2 is just 0.1 of a second. Multiplying these two, we get 8,000, moving the decimal place 1 over. And this is Newton second. And since this passenger is withstanding a car crash in which, in order to stop this passenger inside the car, that's a terrible drawing, from moving forward, we need a backwards force on the passenger in order for this passenger to decelerate, to slow down, and not keep going forward. So the impulse felt by the passenger is going to be backwards relative to the motion of the car. So we can put backwards here because impulse is a vector. We do need directions if we can. And B, now we're on to B. If the passenger is 88 kilograms, how fast was the car going before the crash? So we're going to assume as the car crashes onto whatever it is, that the final velocity is going to be 0 meters per second. And sometimes it bounces back, but we're going to assume it's going to go to 0 and not bounce back. And hey, if it bounces back, that's a larger impulse, according to our last couple of videos, right? So that's more impulse, more force sustained, right? So good thing that the car comes down to a stop, and why we need the crumple zone. Another reason why we need a crumple zone. Nonetheless, we here have the mass, we have the final velocity. We need to know the initial velocity of the car before it crashes. We do have the impulse. So since impulse is change in momentum, And we know that change in momentum is the mass times the change in velocity. And the mass change in velocity here is mass times final velocity minus initial velocity, which our final velocity is 0. This now simplifies to 8,000 Newton seconds equals to mass times the negative initial velocity. Oh yes, which reminds me that the impulse, because it's backwards, I'm going to need a negative sign here for a negative 8,000 Newton seconds. So I'm going to divide both sides here by my mass to get my initial velocity, in which then I can then solve for it. Don't forget the negatives also cancel out. I'm going to be left with the initial velocity is equal to 8,000 Newton seconds divided by the mass, which is 88 kilograms. And after I put it into my calculator, I am going to get 90.90. So that's going to round up to about 1 sig fig according to this graph. If 2 sig figs would be better, that's 91. But here we got 90 meters per second. And that was going forward. Ouch. I don't think I modeled this question properly. Do you know what 90 meters per second is equivalent to in terms of kilometers per hour? That is 327 kilometers per hour. That's a lot. Damn. That's close to the speed of sound. That's close to sonic speed. Yeah, I totally did some bogus question designing here. I'm sorry about that. Not very likely that your car is going to be able to go that fast. It probably experienced too much air resistance to go that fast anyways. But let's see, we got a really fast car. Let's just say the purpose of the question still remains. So here we have example 5. Sorry about that. We found the impulse from the graph using the area, and then using that impulse from the graph, we were able to find the initial velocity of the car before it crashed. Now it is your turn for you to do example 6. So let's just quickly talk about example 6 before I let you dive in, or you can just go ahead and read it yourself. It's part A and B, which there's a graph here below, but I will try to my best to show both. Okay, so here, example 6, I have the same passenger in question 5. That means we have the same mass. He is now wearing seatbelts. Ooh, good for him. The car was traveling with the same speed before the crash, so we know that the initial velocity is the same, 90.90 repeated meters per second. Don't forget to keep all your digits. But the seatbelt helped her to decelerate over 0.2 seconds. Here we have the time. Calculate the average force that she felt during the impact. Okay, and then the next question, B, is use your answer in question A to sketch what the impulse would look like on the graph on the right. Let's say she started to feel a force at 0.5 seconds. So that's where we started off at, and then we're going to assume she sustains the same average force, but then for 0.2 of a second. Okay, so you got to sketch this graph here. Let's see if I can put both questions here. There you go. Okay, so hopefully you can still see that. This is a good time to pause the video and try it yourself. And now I am going to do the question on fast play. To find the average force, we need to start with the impulse equation by dividing both sides of the equation by time to isolate for force average. With our change in momentum at the top, that's just mass times change in velocity, in which our final velocity is 0, leaving us with negative initial velocity. So mass, initial velocity, and time, we can substitute those values in, giving us 40,000 newtons in a backwards direction to stop the passenger from moving forward. To plot this on a graph, we got to use 0.2 seconds total elapsed time, in which the average force is the same throughout that 0.2 seconds. Okay, and here we have the solutions. Notice here we have, since we have a longer period of time in which that momentum has been distributed, the passenger sustains a much less force compared to the 80,000 newtons we got before. This is only half the amount. And of course, the force is applied backwards, so don't forget your directions because it's a vector. And to draw it on the graph, we start at 0.5 seconds. The force is applied over 0.2 seconds, so all the way to 0.25 seconds. And since it's the average force, it is the same throughout the 0.2 seconds. It doesn't change. We can draw a straight line assuming that's going to be the average force throughout. Of course, the graph is not going to look exactly like that. There's going to be curves and dips and up and downs and whatnot. But that's just a general model we can use for such question here. So hopefully this video shed you some light. And of course, don't do what I showed you in the videos at home. I thank you for watching this video. I wish you good luck. And Fat Mama Physics signing